So this next presentation is another in the series of flexible data placement. And I'll continue. The ordering of these talks was really great. I saw and heard the questions that were cropping up in the last presentation. I hope to add some depth on some of the drive side changes. So thanks to the ordering of those presentations. So this is giving some depth on the host workloads, recommendations on the shaping of the traffic, and how to help make sure that you're going to get write amplification of 1, and answering a few of those questions that even popped up in the last talk. Going through emphasizing the backgrounds, and then after some background, some view of the SSD, go into some example write amplification of 1 workloads. So thanks to Mike and John on the great overview of FDP. I can skip a lot of that. So I just have highlighted here a subset of the table that Mike went through in great detail. For me, something that's worth emphasizing here as we start this talk is that ZNS, you'll look at that and you'll be able to have a write amplification of 1 guaranteed, or else you're going to have an error. FDP, you need to do this by a polling methodology. You need to come back and check how you're doing as you're running your host software. Of course, as you get more mature software, you don't need to check as often. And then the other thing, kind of jumping down to the bottom of this table over here, ZNS, because it guarantees write amplification of 1, you can have that potentially compacted FTL. Whereas FDP, we're going to maintain a full FTL mapping in order to be ready to handle any misaligned write or any kind of behavior from the host. So I think that's probably the major thing, since we had such great overviews earlier. From an SSD point of view, I just wanted to put up here an image of an RU, and this is just one example. Earlier question, what is an RU defined to be? Well, in this presentation, for the sake of an example, I'm going to focus on a superblock. Commonly in the industry, a superblock might be described as 1 erase block pulled from every single plane of every single die. So now you're going to be able to have full parallelism of writing to your entire NAND field. That's one reason why superblocks are selected. So I'll use this whenever I'm talking about an RU today. There's other possible implementations of an RU, but it's just easier to have one picture in our minds. And similar to what Mike already described, an RU is going to be filled in order even when the LBA has come out of order. So we are not dependent on LBA numbering. We're going to fill that RU at a physical sizing of the data that's being written. So because I have some visualizations later, I think it's also useful to connect what happens in conventional drives. And so this here, even before we get into FDP, is a view that what we implement inside the drive pretty commonly. We will have this free pool of erase blocks. We form those erase blocks, we gather them together, we create a super block, and so we have that RU or super block, since they're equivalent in this presentation, to being filled. And if you were to write randomly, you could also easily do this diagram here in the center where you've filled your RUs, but you've been invalidating data. So writing randomly, you could order these RUs and you could have one of most valid to least valid ordering, right? And this is kind of a little bit more detail, but you can even simplify it further. And you could even simplify it by taking those, put the free pool of erase blocks on the right, shown as white, and you could put the validity, the RUs, stacking them, showing them as a decreasing valid count, going to the left there. It's very cartoony, but I find it really helpful to give you some visualization of what we are looking at in the drive.
I want to make sure I understand your second bullet. Within an RU, the LBA cannot be necessarily in order. Is that what that means?
Correct.
Okay.
Yeah, so the question was clarification on the second bullet point. And an RU does not require the LBAs to be in order. And yeah, thanks for the clarification. I appreciate the questions while we go through. Yeah, so one thing to acknowledge before I move on from this simplified drawing, not diagrammed is the garbage collection, moving the RUs and garbage collecting them up to the front. And I'm just very simple, but it's a useful little visualization mechanism. So using that, we can now see a visualized NAND and performance transition with write traffic. This is, again, just giving a background so that we're all familiar with conventional drives and what we've seen from performance perspective. But this is a perhaps new visualization tool, so it's worth repeating it for the audience here. Shown here at the top, we have the total physical capacity, and we have a sequentially written logical capacity. So if the logical capacity is 0 to n, you'll see that contiguous and fully valid, and the over-provisioning is collected together and fully compacted. When the prior presentation, they were talking about utilization. This is actually connecting to that. When we have a physical capacity in the drive and the logical capacity of the drive that's reported out, utilization would be how much of the reported logical capacity of the drive is getting used. So the host might choose to allow some host side over provisioning, and they were calling that utilization there. Through this talk, I didn't align to utilization. I was calling it host side OP, but so that you can connect those dots in the prior presentation. For this sequentially written and preconditioned drive, you're going to see very high performance. But as we begin to transition from a sequentially written drive over to a random write, you'll be able to see that because we have compact over provisioning, you're actually going to see those random writes don't immediately hit their steady state value. They actually continue in a sequential performance manner during this transition time. And then eventually, as you run into your minimum over provisioning, so the minimum free pool here is the label, then we have what happens in the drive when you're measuring it. You'll see the random writes reach a worst case performance. So we will have that, and it's partly due to, mainly due to the invalid data points are evenly distributed. And so there's not really a great candidate to do the garbage collection on. So this is where the most data has to be moved, and there's not a great decision on optimal performance there. But eventually we do continue, as you continue with random writes, you'll reach your steady state performance value, which is of course going to be a little bit better. So again, we come back to this randomly written steady state value, and so again to that visualization that came down in the bottom. There was a question last talk on initially isolated versus persistently isolated. So here on this slide, I'm just giving an example where when we talk about optimizing each RUH, you can look at each RUH individually, and you can try and take that RUH and make the traffic equal to write amplification 1 for that RUH. And you can ignore the other ones for that analysis. That simplifies and gives you the boundaries of what you need to look at from a system perspective. It makes it a little bit more manageable if you can move one and then another towards improved write amplification. So shown here is just the picture from the spec, but calling out that when it's initially isolated or when it's persistently isolated, in both of these situations, if you successfully take, this is RUH label X, if you were to take that and have a write amplification 1, then you come back to this where the reclaim group is going to trigger some garbage collection, and you've taken that to 0. There's no need to do garbage collection there. So in both of these, we're going to have the same advantage from a write amplification win. So yes, there are nuances and differences to SSD implementation, but But the takeaway for this talk is that we're going to have the same advantages system-wise on optimizing each RUH. The other thing, to give a visualization, I drew here 2 different systems, but we have different over-provisioning in the SSD. And this is intended here, I wanted to show that, yes, there's a few invalids in both systems. I actually copied and pasted them down, and it's the same drawing. But you can tell that as you fill RUX and you're writing to RUX, it's going to go into the RU labeled A, and you're going to fill that, and then you're going to need another RU from the free pool. And you can see with a lot of over-provisioning versus a little over-provisioning, it gives the context that you don't want to take the drives over-provisioning away, because there's going to be a few invalids that are going to be in the SSD, and those invalids aren't going to trigger the garbage collection at the system, right? That larger SSD over-provisioning allows you to have that buffer, and you won't ever see any over-provisioning in the top system. Whereas the bottom system, because of the small number of invalids, it's at risk of hitting garbage collection very soon. And so this is one of those trade-offs where on the first slide I was mentioning that ZNS is write amplification of 1 guaranteed, but here, because of the possibilities, host-side traffic might possibly have non-optimal traffic, we actually need to allow and enable the drive to be able to manage and cover these kinds of things. It's a recommendable practice there. Because the LBAs are allowed to be out of order, and because the system has, so there's delays in the system side. Sometimes host threads may be trying to interop in a similar region, but they may have different ordering of their threads operations. Or perhaps more importantly, you'll see on the SSD side, we have the freedom on the SSD to pull commands off submission queues at a different rate. We can process them out of order. And so there's a great exposure to small race conditions of ordering. And so even though the host in this example here, try and bring the pointer over, here on the host side, I have an example where the host is writing and tracking a logical RU, what it thinks is happening inside the drive. And it says, well, I've just written 0 to 9999, and whoop, go back a little. So it's thinking that it's writing sequentially, and logically that may be happening in the host software. It might be honest in its operations, but by the time that it reaches through the system, reaches the NANDs, right? This box down here on the bottom is the SSD NANDs. It's not even the SSD controller. By the time that write actually happens, it may have been out of order. And so I've diagrammed here where LBA 1024 actually ended up being written to the NANDs before some delayed LBA 1022 and 1023. So this kind of a nuance is something that, because we don't have an error on operations, we don't know that this happened, right? This could be polled and found out in retrospect through a lot of polling, especially when it's this small and nuanced. And it's not dependable either, right? These are system race condition delays. But if we were to see a host that's running things very tightly, and you come through and as a host and you say, well, logically I wrote 0 to 1023 and it's one group, I'm going to deallocate that group and have perfect write amplification. Well, maybe not, because here inside the drive we have that 1024 LBA actually made it to the NAND. And so when you deallocated, you actually have one stale LBA sitting in one RU on the NANDs, whereas LBA 1022 would be deallocated from an otherwise full RU. So these nuances and race conditions that exist do have a small exposure to non-optimal write amplification. So for these reasons, it's kind of, you'll hear this again and again, but it's, again, recommendable that we allow a little bit of over-provisioning. Basically, as you run for the system, logically, we would expect the system to start deallocating the next RU soon. So as long as you have a little bit of over-provisioning to absorb this, it's going to be negligible, not noticeable, and be totally fine. So yeah, hopefully this is just great visualization, trying to highlight some of the things that we want to pay a little bit of attention to. Yeah, I see a question. It's not track. Oh, sorry. Yeah. So let me go through the mitigations. He's questioning. So if you wanted to mitigate this and you wanted to have perfect confidence that you're going to get correct write amplification, one option is to run QD1. You could do that. It's possible. I don't recommend it. No. The other possibility, if you really, it was important to you as a host to definitely always have write amplification of 1, you could, as you approach the RU, you could pause your processes, wait for all your completions to come back on. Again, you as a host sent LBA 0 through 1023, check that all of them completed, and then move forward. So that is not QD1, but it's also not desirable. So those are two possible solutions, but the reality is what I'm recommending is that you accept the risk and allow a little bit of OP on the drive and proceed forward. This is where I see that as the real solution, right? You don't have to have any software changes. You're just going to have more of a conversation with drive vendors to make sure that it's appropriately buffered there. I see another question.
And that is a per RU statement, like it's not per drive, meaning to limit the number of IOs or keep them as close to 1 as possible. The per RU statement.
So the question is, my statements on doing QD1 are on, their clarification, is it QD1 per RUH? And yes, confirming that it would be QD1 per RUH in order to have this type of traffic. So you hypothetically could have QD1 for every single RUH and have perfect reliance on making sure that you're going to get that expected write amplification. Yes? So just clarifying on the image here, I have it labeled as a logical RU tracking. So this is host side tracking because FDP is a polling. You as a host are going to need to create some constructs on the host side in order to imagine and try and align to what's actually happening on the NANDs. And so logical RU tracking would be that host construct that's pardon me, that's trying to track and copy what might be happening on the NANDs. And this slide is really just emphasizing that what you believe you have sent is not guaranteed just due to those system delays. And so the logical RU tracking is exposed to errors. Is there?
Another way to avoid this then is a possibility is the host could actually have two independent RUHs, and when they're writing over that boundary, they control the switching automatically and to eliminate this whole problem.
Thanks. So Mike's comment, to repeat it for the mic, is a great suggestion. Another mitigation, which I didn't enumerate, he's got a great suggestion, is that for each host thread, you allocate that host thread 2 RUHs, and then as you go through as you fill one logical RU, you switch to the other RUH. When you switch to the other RUH, you'll fill another RU, switch back to the first one. So that is another great mitigation. Again, I still think that most of these are a little bit more invasive into the host software. So while it's true they're great mitigations, the easiest and the one I'm actually recommending is allow SSD OP.
Is there a way to not allow SSD OP in FDP?
Yeah, you could run as QD1. You could run with 2 RUHs.
Is there a way to make the OP go away? There is no way to make the OP go away, right?
No, if you are willing to do the invasive software changes that are otherwise listed, then those will get you a path to reduced OP on the drive. So
The spec
turn on FDP, it doesn't redefine capacity. So there is no P by always.
So the comment, to repeat, is, so make sure I repeat your question correctly here. The comment is that when FDP is not enabled, you have one capacity of the drive. When you enable FDP, you're going to have OP, the same OP is your question. And that's more detail of the spec than I remember. However, I think there's also thin provisioning in NVMe, so I'm not sure that NVMe is disallowing a capacity change for FDP enabled versus disabled. So it's a little bit more detail than I have on it.
It's a question, if you have a drive with FTP off, and you write a certain sequence of IO, you get a certain, like, write application, and then you turn FTP on, and you expect the write application to stay the same. Is that what you're saying?
No.
Okay, sorry, I thought I missed.
Sorry, I may be rat holing out monster.
What?
So Dan, I think that the question or the fact is the fact a drive is shipped by a manufacturer with a certain amount of over-provisioning. And that over-provisioning is the same whether you turn FTP on or off.
So yeah, so clarifying for the mic, FDP is shipped, a drive is shipped with a certain amount of over-provisioning by the manufacturer, and whether FDP is enabled or disabled, it has the same OP is Bill's comment. And I think that is true in most operations, but I'm also not sure that NVMe specifically disallows that. That's
not an NVMe issue, that's a drive manufacturer.
right. Yes, it's a drive manufacturer discussion or implementation. Yeah.
I think the thing is, you have two drives, one with FTP off, or just not even provided, and the other with it on, and then you write the same IO to both of those drives. The idea is in FTP, you've got a lower write time if you're saying it's sensible.
Right.
Follow the appropriate rules.
Yeah, and I have another slide, so I'll hit that exact point in shortly. Yeah. So some of the write amplification equals 1 workloads that I'll be hitting on are listed here. And actually, probabilistic is kind of hitting on the point that Stephen was just getting at, so I'll hopefully give a little bit of depth what he was just mentioning there. And I don't think any of these are astronomically surprising. That's the nice thing, right? They're industry, they're well known. So just circular FIFO, being very clear on what that is, it's looping over any LBA range. And I've heard a lot of questions, and so I thought it was useful to give some visualization of what's happening with a circular FIFO. So when we have this circular FIFO here, I just have LBAs 1 to 4 being written in a circle, and you can see the reds. The reds are overwritten, and really it's kind of a host choice on whether they send a deallocate or they do a direct overwrite. In both implementations, you should still approach write amplification of 1. Because of the way deallocate can be implemented, whether it's recommendable to do the deallocate versus the overwrite can be a discussion that you can have with your vendor. I don't think there's going to be an industry-wide answer that can be put out there for that. Visualizing this, you can see that if we had, here we had that visual example of 1 to 4 getting overwritten, and visually on the NAND, we're going to see that overwrite moving, but keeping all of the NANDs full and compact and moving through an RU. This first example is just 1 RU, and the circular FIFO is smaller than the RU. But these same rules apply for when the circular FIFO is larger than an RU. And this is one of the questions that I've seen come to me. When you have multiple RUs composing this circular FIFO, it still visually is going to be moving through and keeping compact NAND that stays fully valid. And really the only over-provisioning that's going to be used in this is right when you reach the ends of an RU, and you're going to need to allocate the empty RU, add it onto the end, and then keep writing into it, right? So this is a very minimal quantity of over-provisioning used in this circular FIFO. But it is a non-zero. It's one empty RU, right? So this is a simple example, but hopefully gives a reasoning on why you don't need to pay attention to the RU size versus the FIFO size. Of course, as I mentioned earlier, there are some potential race conditions right at the end, but if you continue to write your circular FIFO, they self-resolve in a circular FIFO, so you don't need to worry about that either. So we don't need to restrict to QD1 here. I already mentioned that deallocate versus direct overwrite is going to be a little bit of a question on what is most recommendable. A good rule of thumb is that if you're deallocating, deallocate far in advance of when you will be writing over it, and then over the drive vendors, it should be a very similar behavior. It should be an advantage to deallocate when you're able to send that deallocate early to the drive. Circle back, pulls back, and recommends again some SSD over provisioning or some host OP, which was called utilization in the last presentation. And it's for the same reasons that we've already been mentioning there. So when you have one circular FIFO, we again have this drawing of our one conventional drive that's sequentially written. It is a circular FIFO. So when we look at two circular FIFOs and visually we can see RUHA is one circular FIFO with a small amount of OP, that one extra RU as you circle that's shown there, but RUHB is again compact itself in this simple example. So it's a new visualization of the same effect though. So this comes back to a point that Stephen was already mentioning earlier, but if we had a few RUHs, for example, I have RUH 1, 2, and 3, and the small amount of OP for each of those RUHs being used, keeping them compact, you could have any number of these write amplifications of one, and now, because we have this logical capacity of the drive that's fully allocated, we have a lot of compactly written data, all of the over-provisioning for the drive ends up coming to that final RUHN. And so now we could have RUHN with a small logical capacity, but a very large over-provisioning available for its use case. In the event that RUHN is not receiving write amplification 1 traffic, it's got a lot of over-provisioning. And so from a probabilistic standpoint, it is very reasonable for you to drive write amplification 1 of many of your RUHs and then get a greatly reduced system write amplification just due to that over-provisioning being available for the rest of the drive, or the rest of the RUHs that are not well behaved. So it is probabilistic, so you're not necessarily guaranteed definite WAF equals 1. It's a trending down, right? But very large over-provisioning for small logical capacities is reasonable. Oh, and actually tying this back to the last one, the last talk, this is where the small item engine that is dealing with metadata and small hits, if it's a small logical capacity of storage, this is a good solution where you can get to a very good write amplification just because you've allocated a small amount of capacity to that random writes of that small item engine.
Dan, can I ask, why don't we ship drives with 300%?
Yeah, I would like to ship drives with 300% over provisioning. I think that's,
I think that solves the write-up.
yeah.
Do it yourself. Only allocate an namespace of 30%. You can do it yourself today.
So this actually, I just mentioned the small item engine from the last talk. I don't believe it's implemented. I think it was at a paper submission, but there's actually discussion where CacheLib was going to implement something called Kangaroo, which is effectively doing this modified circular buffer. So tying the relevance of this slide into that small item engine there. Essentially, this is what I'm calling a modified circular buffer. I have the head where the new valid data is being written. Any new cache entries coming into this small item engine might be inserted there. But on the tail side of it, we have this tail progressing ahead of the head, and it's effectively making sure that, since this is a cache, we wanted to make sure that we're gonna get rid of anything that's still valid in that small item cache. So shown there is a dark blue where the tail is discovering it's still valid, and it says, okay, what are we gonna do to decide about this? And so they would either move it out to a more permanent residence cache, or they would otherwise handle that. And so one thing I'm starting to describe here, and I think is a good way to think about it, is that for reaching write amplification of 1, you actually have two options. One is that you look very closely and you comb through your write incoming traffic. But to me, this one's an easier one to think about. The deallocating assurances is another way that you can, as a host software architect, you can think about making sure the deallocates are fully happening. And it's the same thing, it's the same result, but it's a different way to construct your host software. So the other thing I'm calling out here is that while we have invalid cache data, the reality is we don't necessarily need to send to the drive that we're going to deallocate it. If you're going to overwrite it with an LBA, it's self-invalidating when that overwrite happens. So there is an implementation decision on choosing to send the invalid cache data down to the drive, or just sitting on those and waiting for the overwrite to happen. Both cases, we will still be able to reach write amplification of 1. Yeah. Something that I think is actually a little bit more, the most common deployment that I'm expecting for FDP is going to be integrated into a log structured file system. So RocksDB was the discussion example from the last presentation. This is a little bit more generic, not focused on any of a specific application. But overall, these log structured file systems are really common in the ecosystem because it's an advantage for both HDD and SSD to write sequentially. So as the objects are written, they're appended onto an RU using an RUH handle, and it just continues to fill up sequentially writing. Of course, because these objects are written and appended at the end, the reads are going to be random. This is a strength for SSDs, so we're good with that. We aren't too worried. There's a lot of different names. Like I didn't know really which one was most common, so I just started using host extent, but I did see that there's tons of other names out there in the literature. And of course, there's higher level protections that could be applied at the system level. Erasure codes, RAID, CRCs, those kind of things. And we, as an SSD, we just see that as incoming data. It's all contiguous for us. So interacting with an FDP SSD, when host extent can be set up to be equal to an RU, this is where it's easiest to visualize the advantages. Is there a question or no? Okay. So setting host extent equal to an RU is the easiest to visualize. And this is where I also see it as a deallocation assurance to achieve a write amplification of 1. We can see this host extent shown here, and I have some invalid data diagrammed there. And so now when we take these 4 RUs that are diagrammed and you do the file system level garbage collection, you're able to deallocate all 4 of them together, and that'll provide your write amplification of 1. So the deallocates are not required to be communicated to the SSD. There's actually a little bit of an advantage to not communicate the invalid data to the SSD, because then they won't be seen as something that's potentially available for garbage collection. So you can actually choose to allow the invalid data to be tracked in the file system, but waiting for full RU deallocations is an option that's well worth evaluating. Again, because of that risk of that over-provisioning, of that garbage collection, it is again an advantage that I recommend to allow reduced utilization from the host side, or allow the SSD OP to remain in place. Inside, so this talk has mainly focused on how we can get to write amplification of 1. I think that this slide is kind of a teaser. I hope to come to another conference presentation in the future. We've been evaluating internally what happens when we have a log structured file system where the host extent might not match up to the actual RU. And these could be due to many reasons. Maybe there's a vendor to vendor mismatch. There's a generation over generation RU change, or maybe you just plain had the software developed before or in separate development than the SSD. So this mismatch happens a lot. And I think that this is more, again, it's just a teaser, but we found that write amplification of 1 happens every single time the host extent was equal to multiple of the RU size, which was a nice finding. You can't plan on that coincidence, but once you have that pointed out, it makes a lot of sense, because it's going to deallocate and free up a lot of the SSD RUs all at once and available for their rewriting. And then we also are finding large host extents are a general positive recommendation and drive towards write amplification of 1 as well. More complete data on this I hope to bring in the future for a better in-depth talk. But again, we found also in our simulations here already, another positive support for allowing system-wide OP, whether SSD or host utilization, host-side OP. So just summary here, gave a few example workloads and that achieve write amplification of 1, and then we also spoke through a few examples and described it as a write, an overwrite, or perhaps deallocate assurances in order to think about it as a host that's going to try and achieve write amplification of 1, and gave many examples of why advocating for that SSD OP and reduced host utilization there, and recommending as well the deallocations before LBA reuse is a positive thing to do if you're going to be sending the deallocations to the drive. And that's my presentation. If there's any more questions. Yes? Slide 14. This one? Yeah. What's the impact of, what is the impact of not having an aligned extent to RU size? What is the impact? So this is why it's a teaser. The full discussion on the impacts is not one slide worthy, and the results for that came in after I submitted for this the abstract for this title. So this is a little bit of a teaser. The big takeaways were we do recommend larger host extents. That's a common finding that we found throughout. If you're going to have a mismatch on the host extents and the RU, bigger is better on the host. That was the major thing that's through and through a good recommendation there. But otherwise, it turned out to be a little bit more nuanced, and I was surprised at it. So I'm really actually looking forward to getting that in front of others. So, but yeah, it wasn't really aligned with a Write Amplification of 1 findings. It's not quite, yeah. So thank you for that question. Yes?
Is it expected that the host write amp might increase given the hosts are trying to maintain the RU size and they have to write the entire RU all the time?
So the question is the host write amplification increased because they're trying to match up to the SSD RU sizes? And that's where we started to get into this, right? We're trying to say, what is the cost system-wise? If you're going to have the GC, for example, shown on this image, we see the host extent goes a little bit more than 1.5 through the second one, right? It's not an alignment. So if they ignore it entirely and they just manage it on a host extent, does that go to trash? And the answer is no, it doesn't go to junk. It doesn't get worse. There is an improvement through and through. There was an improvement, but it wasn't always, it doesn't go to 1. And we actually were able to understand why it reached a median between conventional SSD random write level of garbage collection compared to Write Amplification of 1. We started to understand those. But it still is going to be an improvement, is a big thing, right? It's still recommendable. It never got worse.
The only comment I'll throw out is you're not going to get a Write Amp of 1 no matter what you do. And the reason why I say that is there's other things besides garbage collection, like refresh the NAND that happens. And we don't get to shut that off with FDP commands. So it's going to be just, I don't know, Write Amp of 1 is almost like, to me, feels like infinity. It's like, it's a conceptual concept that we'll get closer and closer and closer to, but we'll never precisely nail.
Yeah.
And like I said, you can't even really get there for other reasons.
Yeah, so just to repeat for those that are on the recording, Stephen was commenting that you can't ever really get to Write Amplification of 1 because the real world happens. We have the NAND management and a lot of other system level things. I think like even on the system side, there's the metadata, right? So I think, yeah, giving an example of moving that small item cache into a modified circular buffer is a help, but that's still another write stream. That's still more writing. And you still gotta, when that cache entry is still valid and your tail catches up to it, what are you gonna do with it? That's still a system-wide impact on write amplification, but it might be very minor, right? So I agree that it's all an improvement, and yeah, so thanks. Yes?
Like you said, I think Write Amp 1 is impossible, but it's still good to use Write Amp. So here we try to analyze many different methods, and the previous talk focused on how to build the application. But in practice, in real world applications, which method gets you the most reduction? Is it column fault separation, or is it the trying to do the GCI double sign, trying to align
Yeah.
the allocates in practice, what gets you the best?
So the question is, what in practice is getting better towards optimal? And the two contrasting examples that you brought up were hot versus cold, and aligning the write amplification to 1. So with ZNS, they have the communication of the heat on zoned lifetime hints. And so that, as an SSD implementer, that is a good thing for me to look at that hint, to put it on the correct NAND, to make sure that it is going to be aging for hot versus cold. And so I will, through my management of NAND, I'll put a better and more intelligent placement of NAND. So that is an advantage, but through and through, the biggest win is to start out. The first order win to me is looking at write amplification and reducing that. And the management of where you place things on the NAND is the next layer that you pull in. And it seems very reasonable that FDP could have the same hint of lifetime if you were to provide that. But I think that my recommendation is to focus on that write amplification as a first. And even if, for example, you look at FDP already has, here is an example on that bottom left. We could have RUH1 as very hot and RUH3 as very cold, and it's still separated, and because it's separated, naturally you're going to have more system level recycling of what is happening over on RUH1. But system-wide, RUH3 is going to sit still more often. So because of the separation that's already happening, that RUH separation is already giving you a win on how much is getting intermingled. So I think that is, again, that is my recommendation on where things are. I think, more modeling could be valuable to prove that, because what I'm saying here is more of a intuition than I don't have data to show you this right now.
Does anyone know if the QEMU models for FTP, they give you a sense of OP, assuming a given drive structure?
So the question is, does QEMU give you a sense of OP when Write Amp? And this came up in the last talk, and the answer from Klaus is that no, the system, the host side write amplification of you thought, so RocksDB example, you write to RocksDB, how many writes actually hit the SSD? That write amplification is tracked, and QEMU is very valuable for doing that, but there isn't a model of internal drive write amplification that's there.
I know there's an entire tree NVMe drive model from one of the universities that does actually give you that kind of thing, but it's not in the
Yeah, so thanks, Stephen. So just repeating for others, there is a SSD model that's out there from one of the universities that could be connected up to provide that extra information. So. Yeah. So I think that's everything. So thank you.